Okay, we're going to continue on here and finish up naming, I think, and then it's spring break at that point, I imagine, right? All right. So last time we got into really ionic nomenclature, and when we talk about sort of ionic compounds, as we did with bonding, they do involve always a metal and a non-metal. And as we talked about last time, pretty much when you're naming, that metal is really always the most important thing. So if you ever have a metal involved, that is always where you should look at in terms of how you should go about naming it. Now, what is the difference in here? We talked about a type 1 sort of metal and a type 2 metal. And really, type 1 metals have fixed positive charges. And those are obviously the metals there. That's going to be somebody from basically group 1, 2, 3, which is usually aluminum, zinc, cadmium, or silver. And again, those are three transition metals, but they do possess basically a fixed positive charge. Now, a type 2 sort of ionic compound or metal is one where we have a more variable positive charge. These are usually your transition metals, obviously, except those three we just listed above. And just to the right there of the transition metal region, again, below the staircase where we have things like lead and tin, PbSN, in that general area on the periodic table. Because they have a variable positive charge, you do have to do sort of one additional step when you name those guys. So type 1 compounds, you pretty much just go with the whole name of the metal. And remember that our non-metal, we dropped the last part of the name and we put IDE in there. Also remember, as we talked about, that you should never, ever, ever use really a prefix whenever a metal's involved. So again, that's a really good way to remember not to use any type of prefix is if you see a metal, you definitely should not be using it. And I mean, for something like CaBr2 that we looked at, again, this is metal, non-metal, group 2 fixed positive charge, type 1. This would be calcium bromide. Once again, no dibromide here. It doesn't matter in terms of ionic naming how many of either of those guys you have, how many of the metals, how many of the non-metals. We never use prefixes here. The reason we do obviously have more than one Br is because when we look at the ions that make this up, calcium with a +2 charge is our cation, and our anion is bromine, which is group 7, has a -1 charge. And again, the 2 means we have two of those. And as I also mentioned last time, it does not mean you have that. So that is incorrect. Yeah. So again, you just have two of the Br minuses in this case. Now, type 2, because it can have a variable type of charge, the metal, we do have to sort of figure out what the charge is. And we still really name it the same way. We do use a whole name of the metal still. We still go our non-metal with the IDE at the end of it. But the additional thing we put in there is some Roman numerals. And once again, the Roman numerals is the charge on one of the metal positive guys by themselves. It is not how many you have of them. It is not the grand total of all the positive charge. It is just you took one of the positive guys out and what the charge is. The thing that we talked about is you will always know what is attached to. So like we saw this example, for example, here. Again, metal, non-metal tells you it's ionic. Always look at the metal. We again find iron, like we talked about last time, in the middle of the transition metal region, which again should tell you it has a variable charge and you need some Roman numerals. So as I mentioned, you will always know the charge on what it's attached to. Chlorine being group 7 -1. There are three of them. And again, if you just add up the overall negative charge, that's -3. Remember, always when we put a positive ion and a negative ion together in an ionic compound, the overall charge needs to equal 0 in the simplest way possible. And in this case, that would mean that the iron is carrying a +3 charge here to balance it out. Then we could go into our naming, iron, Roman numeral 1, 2, 3, once again for the charge. And even though we got 3 of those guys, no prefixes here because, again, you can remember if there's a metal involved, so never a prefix in that situation. Any questions on any of those things we talked about last time there? All right, then yeah, I'm sorry. Absolutely. Absolutely. It is the charge if you took out the positively charged metal and just what that charge is on one of them. So very commonly confused by people is, again, they think their Roman numeral means like how many metals they have or something like that, or how many of those guys they have. It does not mean that. It means like if you took just one of them out, what the actual number of that positive charge would be. And again, not the grand total of all of them added together, just what the one individual one would be. Yep. Other questions? Okay. All right. So that's type 1 and type 2 ionic compounds. Really, the distinction when you have a metal, which is really what you want to look at, is pretty much that question of should I lay up some Roman numerals or not, basically, and that's sort of what you want to decide. They both pretty much are named the same on the rest of it. So again, here is those things we just talked about, which will help you decide. Pretty much if you got that type 1 metal, or group 1, group 2, or group 3, again, silver, not lead, silver, zinc, and cadmium, also fixed charges for our transition metals. No Roman numeral needed. Once again, as we talked about last time, we don't need a Roman numeral for those guys because no matter what the situation is, they're never going to form any other type of charge than what they always form. So again, like we talked about sodium, you could hook sodium up with whoever you like. It's always going to be +1. It'll never be any other number. So that's why we don't need to specify when we name it that it has a +1 charge. But iron, like we just did there, in certain cases, like we just saw, it could be +3. In other cases, it can be +2. So you do need to include that Roman numeral to tell people, hey, in this case, we're dealing with the +2, or in this case, we're dealing with like the +3. So again, that's really the purpose of you need the Roman numeral. I think we also saw last time there's sort of an older way of doing type 2 naming, which again, we're not going to really follow in this class. And again, you may see some of that like ferric, cupric, cupros, again, sometimes used, but we will strictly go with Roman numerals in here. All right, so why don't you take a moment here and name each of these and see what you come up with. So let's take a look, see how you're doing. Again, remember when you're naming, you just want to kind of identify what you're dealing with. So Hg is mercury, which is a metal, and oxygen, which is a non-metal. So once again, that should tell you it's an ionic compound. So really, whenever a metal is involved, like we talked about, that's really what you should focus in on. And if we find mercury right there in the transition metal region, which tells us it most likely can have multiple types of charges. That tells us it's a type 2 compound. So we do need to figure it out here. So we don't know what mercury may be, but we do know oxygen is group number 6, which means it does have a -2 charge. Once again, to balance it out, it will have a +2 charge. And this would be mercury Roman numeral 2 because of the charge here. And again, this would be oxide. By the way, mercury is one of those weird ones we talked about last time. I know this is mercury 2 because what's missing for it to be mercury 1? The 2 on the bottom, right? So that was the one that had the 2 on the bottom and the 2 on top. So it's one of the weird ones. So remember, this is mercury 2. This, again, if you see it, would be mercury 1 in this case. All right, taking a look at the next one. We got metal, magnesium, bromine, nonmetal. Looking at our metal here, that is group number 2, which means it's a type 1 compound. And really, that's all you need at that point. We just need to use the whole name. which would be magnesium and bromide. And again, here, no Roman numerals needed because the magnesium has a fixed +2 charge in this case. The magnesium is +2. Our anion here is Br- in this case. And again, there's 2 of them to balance out the charge in this case. Here we look at Li, which is lithium. Oxygen non-metal, so that tells us it's ionic. Lithium again, which is the metal, is what we want to look at, and it is group 1 on the periodic table, which once again means it has a fixed +1 charge, and that also makes it a type 1, which means we don't have to worry about charges or Roman numerals. It is just lithium oxide in this case. Once again, no prefix needed here for the lithium. Again, the way to remember that is metal involved, no prefix. Again, we do have the 2 there because we basically have 2 positively 1 cations to balance out the -2 anion that is present in this case. Lastly, here we have chromium, metal, fluorine, which is a non-metal, and it's ionic. Chromium there in the middle of the transition metal region there, 24. That means it does have a variable charge, so we need to figure it out. Looking at what it's attached to, which is group 7, we have a -1, and there are 2 of them. So -1 is a -2, telling us that in this case the chromium has to be +2 to balance it out to 0. And that gives us our name now of chromium Roman numeral 2 once again for the charge. And even though we do have, again, 2 of those, we don't use any prefix. Any questions on any of those there? Okay, then let us talk about the next type of naming, I think. Type 3 compounds are different than what we've been talking about, which is ionic. Remember, with ionic compounds, we have a transfer of electrons. That is when we create ions. In type 3, these are actually covalently bonded guys, which means they're going to be sharing electrons, and they're going to be between 2 nonmetals. So those 2 nonmetals will share electrons, and we will also name them differently as well. This is, by the way, the place for prefixes, if I could write that big enough. So that is the place where we actually do use prefixes. So this is the time and the place to use prefixes. No other place pretty much other than in this situation right here where you have 2 nonmetals together sharing some electrons. So they use prefixes. Again, we'll see a chart, but we have mono, which is 1. We have di, which is 2. We have tri, which is 3. We have tetra, which is 4. We have penta, which is 5. Hexa, which is 6. Hepta, which is 7. Octa, which is 8. Maybe a little nona, perhaps, for 9. Maybe deca, could be making it up. We'll see. Deca is 10 in this particular case. So we use these prefixes, and the way we go about naming these are pretty straightforward. The nice thing about these guys is they're sharing electrons, which means there's no ions, there's no charges. You don't have to balance out charges. You don't have to figure out what the charge is on anybody. You essentially just need to pick the right prefix and use it if necessary. So the way that we do this is if needed, we use a prefix on the first name, and we use the whole name of the first element. We then use a prefix on the second name, and the second name ends just like it's been ending. We kind of do the IDE at the end of the nonmetal on the second one. So it's basically prefix, whole name, prefix, IDE ending. Just count what you need. Now, there are a couple things that happens when we're dealing with prefixes. One of the main rules is we actually do not use mono on the first name, but it is okay on the second. So no mono on the first name, but you could use it on the second name. The other most common thing that occurs is we end up getting, in certain cases, two vowels that back up to each other. And the most common example of that is we get like two O's that back up to each other, are an A and an O. And these guys come from the ending of the prefix, and the next letter is the beginning letter of the element, basically. So we get these two guys here. When you get like two O's that back up to each other, usually we get rid of the O off of the prefix. And if you get an A and an O that backs up to each other, we also usually get rid of the A off of the prefix. So an example of this, for example, would be capital C, capital O. That is carbon and that is oxygen. They are both nonmetals, which should signal to you you're in a type 3 situation, and then it is all prefixes correctly here. So I have one carbon, prefix is mono. Should I use that on the first name? I should not. So because I'm not going to use it on the first name, we're just going to simply use the whole name there, the first element, no prefix in this case. We have one oxygen, prefix for one is still mono, and we can use it on the second name. And if you put that in there, you get mono. Again, the second name there becomes IDE. And if you just wrote it straight up with the prefix and the name, you would end up with carbon monoxide. We don't really call it carbon monoxide, we call it carbon monoxide. So we will get rid of the O here off of the prefix, and this really should be carbon monoxide. So occasionally, and a lot of times with oxygens, where this is going to probably happen, you'll get two O's that come back to back from the prefix to the element name, are an A and an O. In those cases, we do just drop the prefix vowel at the end. Oddly enough, two I's are okay, but an O and O, an A and O, but two I's you're usually pretty good on. It's okay on that situation. Question on that there. Again, these are definitely the easiest to do, but they also are the ones people screw up the most on because they think it's got to be more difficult or something like that. So they do all kinds of weird things they shouldn't. So again, nice thing, don't have to balance anything. There's no charges. Simply just count how many are there and use the appropriate prefix. All right, so as I mentioned there, we don't use mono on the first name, but it's okay on the second. I will say, I think we talked about it last time, but just to reiterate, one of the nonmetals that kind of doesn't follow type 3 naming is hydrogen, when you have hydrogen. And a reminder that hydrogen over there, kind of in group 1 or hanging out on top of group 1, is also named very much like a type 1 compound. It's oftentimes thought of as being like H+. And if we have something with hydrogen, again, we just simply use the name. So hydrogen chloride here. We don't really use prefixes or anything like that with it, even though they're technically two nonmetals. It's almost named more like a type 1 sort of ionic compound, even though everybody's sharing electrons there and stuff like that. And again, even if you had two hydrogens, which you hopefully won't smell this too soon until you get to 1B, a little hydrogen sulfide gas. By the way, don't smell it when you get to 1B as well. That's why they throw you in a fume hood. Hydrogen sulfide, once again, even though we got multiples there, we still just call it hydrogen sulfide gas and stuff like that. So hydrogen is sort of an exception in terms of how you name it. It really does sort of just follow that type 1 sort of naming. Here again is our list of prefixes. Now, as we just saw a second ago, again, we oftentimes will drop that A from the prefix and the O, and again, not get those two vowels to kind of back up to each other. Once again as well, something like water, which is H2O, is how you should refer to water. NH3, which is ammonia, again, how you should refer to it. And I think we added methane to the list here, which is what comes out there when you light your Bunsen burner. Methane definitely as well. So those guys should always kind of go by those names. Again, no dihydrogen monoxide or anything like that for water, because nobody wants to drink a glass of that, right? All right. All right, so why don't you give these a go, see what you come up with. Let me give you some names to write some formulas. Let's just make some stuff up that doesn't exist. So nitrogen pentoxide. Let's do carbon tetrachloride. Let's do dioxygen hexasulfide. Definitely probably doesn't exist. All right. We want some names on the left there, some correct formulas on the right. Okay, so let's take a look at these. Like I said before, these really probably should be the quickest ones that you name and write formulas for. So when we look at this, I is a nonmetal, O is a nonmetal. So that tells you it's type 3. And at that point, you should be really happy because, again, there's nothing to balance, nothing to figure out charges. You simply just need to pick the right prefixes. So I2 means I have 2 iodines there. So prefix for 2 is di. Iodine, we use the whole name there. Prefix for 7 is hepta, and oxygen gets the IDE treatment at the end. Here we will drop the A off of the hepta there so we don't get the AO sort of combination that backs up to each other. Any questions on that one there? Next one, again, we look at it, which is CO2, carbon nonmetal, oxygen nonmetal, type 3. We have just one carbon, which, as we talked about, we will not use mono, which is the prefix there on the first element. So we just use the whole name, which is carbon. There are 2 oxygens. Prefix for 2 is di. And once again, the second guy does get the IDE treatment at the end of it, and that will get us carbon dioxide in this case. Same thing here, phosphorus nonmetal, chlorine nonmetal, which tells us type 3. We have 1 phosphorus, not going to use mono again, so phosphorus. And we got 3 there, Cl, so prefix for 3 is tri. And again, our chlorine becomes just like normal chloride at this point. Any questions on any of those names? Probably the thing that should take you the least amount of time is the stuff on the right there. So if you're given a name and you need to write a formula, you should look at it and go, I see prefixes, so the only place that could happen is here. So you don't have to balance out anything, but pretty much write what it says. So di is 2 and nitrogen is N, so N and 2. Penta is 5, oxygen is O, O5, and you are done in that case. Yeah. Next one is carbon. We don't see a prefix, but we do see a prefix on the second name, which tells you it is a type 3 compound. No prefix on the first name tells us we have just one of those, right? So that would be a carbon. And tetra is 4 and chloride is Cl. And there you go. Again, nothing to balance in terms of these. Just got to do what it says. Lastly, dihexa, prefix is type 3. Oxygen, dioxygen, that's 2. And hexa is 6. On whatever that made up thing is. O2 S6 in this particular case. Any questions on type 3? So again, people always want to use prefixes everywhere. This is where you should use it only, yeah.
For naming it, well, it doesn't solve this. They have nitrous oxide. How can we call it nitrous oxide?
There are common names for things, and one of those is that, for example, coming up maybe, unless they threw out that lab, I don't know. But there's a lab where you use manganese dioxide. But even though manganese is a metal, which should have a Roman numeral, so it's a sort of a name that's been used for a long time, they still use that. But it really should be like manganese 4 oxide is really the name of it. So there are certain things, not a lot in sort of general chemistry sort of naming, that they kind of use those kind of older names. But when you go, for example, if you go on and take organic, there's a ton of stuff that there's like historical names, common names that people use. For example, there's like 2-propanol, which is isopropyl alcohol, which is rubbing alcohol. They're all the same thing, right? So there's like 3 names for the same thing. So it's very common, yeah. Yep. Other questions? All right. So review of what we've been talking about here. Again, type 1, type 2, they're going to be ionic. The decision there, because there's a metal involved, that's what you want to look at. And again, the decision is Roman numeral or no Roman numeral. Type 3, that is prefixes all day and only prefixes. Nothing to figure out, no charges or anything like that. All right, the next thing we're going to talk about are compounds that contain polyatomic ions. And polyatomic ions are kind of weird things in a sense. They are groups of nonmetals that are covalently bonded, so they're sharing electrons. But based on kind of who they're sharing electrons with and how many they're sharing electrons with, they're going to unequally kind of share those electrons that they actually sort of gain, in a sense, like an overall negative charge. So our charge, I should say. But they're actually covalently bonded things that have charges, which makes them ions, basically, in this case. So an example of that is NH4NO3. When we look at NH4NO3, we actually could break it right about there. And this actually contains two different polyatomic ions. This guy over here is NH4 plus. So that one nitrogen and four hydrogens always stays together, and they always move around as a whole unit. And that is because they're actually sharing electrons here. But that entire thing has a +1 charge. This guy here is NO3 minus. That one nitrogen and three oxygens also stays together as a whole unit and never breaks apart into like the individual elements. And it has a -1 charge. These are both ions, and it defaults back to what we talked about with ions, which is when we put them together, it needs to equal 0. And that is why when we look at it, we are ultimately putting +1 together with -1. So we just need one of each, which is why our formula looks something like this, where we have just basically one of each of those guys. By the way, we drew these, I think. Maybe you drew it earlier today. I'm not sure. We'll see. You got a Lewis structure like that. That is ammonium. And that should not be confused with ammonia. And our nitrate looks something like this, perhaps. And again, they are sharing electrons, +1 and -1 there. Again, is why they balance out to just one of each of them. The thing with polyatomic ions are they have a name that goes with them. And this guy is the ammonium ion. Again, not to be confused with NH3 that doesn't have a charge. That is ammonia, which is not a polyatomic ion. So do not get those two confused. This guy here is what is known as the nitrate ion. The good news or bad news, I don't know, with polyatomic ions is we pretty much just use the whole name. We pretty much just use the whole name of the polyatomic ions when we go and name it. So that is ammonium nitrate. So polyatomic ions, regardless of how many you have, you never change the name. It has really like a fixed name that goes with it. They also have fixed charges. So nitrate will always be -1 no matter what the situation is. Ammonium will also always be +1 no matter what the situation is as well. Now, I will say that ammonium here is probably one of the few positive polyatomic ions that you'll come across. Most polyatomic ions are actually negatively charged. So I would say probably 99% of the time when you're dealing with a polyatomic ion, you will probably have it hooked up with a metal. So most of the time you'll have a metal and a polyatomic ion together. And once we have that metal involved, just like we talked about earlier, that is basically where you should look. And really, again, here you need to decide based on the metal that's there, do you need a Roman numeral or do you not need a Roman numeral? So you sort of default back to type 1 or type 2 naming because the metal's involved. The polyatomic ion is just the name of it no matter how many you have of it. So for example, if you have NaNO3, we break that guy up right about there. That is our sodium ion, and that is our nitrate ion. And in this case, it is the metal we want to look at, which is group number 1. It has a fixed positive charge, which makes it a type 1. And that means we would just call this sodium nitrate. Again, no need for a Roman numeral because the metal is a type 1 metal. Now, if you took the same guy and you put it together with our iron that we saw earlier, this is a metal in our polyatomic ion. Here we do need to figure out what the charge is because the metal is the most important. And again, that's a transition metal, which means it can make multiple types of charges. So the iron here, we would do the same thing. Once you learn the formulas, you'll know nitrate is -1. There's how many of those? There's actually 3 of them in this case. And if we add up our negative charge, -1, -2, -3, we know again here that the iron has to be +3 to balance it out. And we would call this iron Roman numeral 3, once again for the charge. And just like we did with type 2 and type 1, doesn't matter how many polyatomic ions you have, you just roll with the name of it, which would be nitrate. So this would be iron 3 nitrate in this case. Question on that there. And I would say probably 99% of the time, that's what you're going to probably be dealing with, metal and those polyatomic ions together. By the way, why did I lay me up some parentheses there? Why did I not just write the formula like this? Yeah. Yeah, I hope you don't have 33 oxygens. Yeah, so if you write the formula like that, you're implying you have 33 oxygens and just 1 nitrogen, when in reality, as you can see, you got 3, 6, 9 oxygens and 3 nitrogens. So whenever you have more than 1 polyatomic ion, you do need to put parentheses around the polyatomic ion and to the bottom right there, how many of those units you basically have. So that's another thing to watch out for when you're writing formulas there. For things that contain polyatomic ions. Question on that there. All right, so there's a list, of course. There's a list. Here's a list. We'll take a look at this list. There's another list in case you missed the first 6 of them. All right, so this one I think is on Canvas as well in the exam 2 module where all the naming stuff is. So you do have to know these, as they again want you to know everything here. So you do have to know these. You do need to know the formula and the charges. And again, obviously you need to know the name. You do need to know the charges so that you can put things together correctly. Now, there is a way that you could kind of group these things together to help you learn them or make it a little bit more manageable. There are typically groups of like 2 or groups of 4 that are related to each other. So for example, if I look at NO3 minus that we just looked at and our NO2 minus, our NO3 minus is nitrate as we just talked about. The NO2 minus is nitrite, ITE. We have something like SO4 2 minus, and that is 4 oxygens, 1 sulfur with a -2 charge. That is sulfate. We also have SO3 2 minus. Once again, sulfur and 3 oxygens, -2 charge. That is sulfite. Now, in a group of 2, which are related to each other here, you could look at something like this here. We have 1 nitrogen, 1 nitrogen. We have a -1 charge, -1 charge. The only difference between those 2 is the number of oxygen. Guy on the bottom there has 2 oxygens. The guy on top has 3 oxygens. And same thing over here. The only difference between sulfite and sulfate is the number of oxygens. The charges are exactly the same. They both have 1 sulfur in this case. What you could hopefully see is the one with the most oxygens ends in 8. So 8 is usually the most oxygens in a grouping. The least number of oxygens end in ite. So you can either kind of learn them all individually, or what you can do is, for example, learn all the 8s. And then if you need the ites, you just take off an oxygen, right? Or you can learn all the ites, and then if you need an 8, put on an oxygen. Charge stays the same, everything else stays the same. You just basically move it one oxygen up or down, depending on which one you learned or you know in your head, and you can kind of adjust to it. There are also groups of 4 that are related to each other. And the most common group of 4 is right about here. We have ClO4 minus, ClO3 minus, ClO2 minus, and ClO minus. Now, every single one of these has a -1 charge. Every single one of these has a chlorine. The difference here, once again, is the number of oxygens in this grouping of 4. You could do the same thing in a grouping of 4. You could break it up by 2s. To the right of that line, those are the ones that have the least number of oxygens, which means we should know it should end in 8 or ite if it has least. Ite. So this would be chlorite. This would also be chlorite. You clearly cannot have the same name for 2 different things. So in a grouping of 4, the one with the least number of oxygens out of all of them, in addition to ending with ite, will actually start with hypo. And hypo means less than. So that is hypochlorite, chlorite. On the left of that line, these are the guys that have the most oxygen, which means they should end in 8. So this would be chlorate. This guy also should kind of end in chlorate. Same deal, we can't have 2 names, or the same name for 2 different things. In a grouping of 4, the one with the most oxygens will actually start with per, and that is perchlorate, chlorate, chlorite, and hypochlorite. By the way, that Cl is a halogen, which means you could actually swap out that Cl for any halogen, and it's named the same way. So if you had to guess, what would BrO3 minus be called? So Br is bromine, right? So that would be bromate. Yeah. What would like IO3 minus be? That would be iodine, and it would be iodate. Yeah. So you could swap out any of those guys for a halogen. They're basically named the same way. Just kind of change the chlor part of it to whichever the other halogen part of the name is, and you could do that as well. So this also works, for example, with memorizing one thing and knowing how to adjust. So for example, if you memorize chlorate with the 8 part, right? And you need chlorite, you should take 1 oxygen off, right? You're down to chlorite. And if you need hypochlorite, that's now 2 oxygens off of the original guy, right? So you take 1 more oxygen off, you'll be there. Or if you need perchlorate, that's above chlorate, you just add an oxygen. So a good way to do this is to know how to sort of adjust the oxygens up or down, and just kind of memorize one and kind of know how to adjust whichever way you need to adjust depending on what you're doing. So that's a really good sort of way to do that. Question on that there. Yeah.
So for the chlorate, if that's for would hydrogen peroxide in each O4?
Would say again, hydrogen? No, hydrogen peroxide actually would be H2O2, and that's because actually peroxide is this guy. It's actually a polyatomic ion. That's peroxide, actually, which might be on here somewhere, maybe. I think, yeah, right here. So that's actually peroxide. I actually wrote it right next to it there. So that's peroxide. That's actually a polyatomic ion itself. So that's what it would be. Yeah. Yep. Yep. And again, that's also why we need 2 hydrogens for it, because it has a -2 charge to balance it out. And kind of like mercury too, the 2 stays there on the bottom as well. And that's how you know it's peroxide and not really just oxygen in a lot of cases as well. Now, there's a few other things that you'll see on this chart that sometimes is done. If you take CO3 2 minus, that is carbonate. And if you add an H plus to it, it becomes HCO3 minus. We added an H plus 1 and minus 2 equals a minus 1 charge. And what we basically did is add a hydrogen to it, and that is what is known as hydrogen carbonate. As to like an earlier question, some historical name, some people don't use hydrogen, and it's been used for a really long time. Instead of hydrogen, bi is used. And this is sometimes referred to as bicarbonate as well. And that is also very commonly still used, like sodium bicarbonate. You buy some baking soda, basically, right? So that's some sodium bicarb. So bicarbonate used a lot still. I would say also the sulfate version of that, which might be up here somewhere. Where is it at there? Right here. The hydrogen sulfate, also called bisulfate, is also used still today a lot. So you should know at least those two names for sure, because I would say those are very commonly still used a lot, bisulfate and bicarbonate. In addition to hydrogen carbonate or hydrogen sulfate, you could do that. Some other things that you might see is there are some polyatomic ions that actually do end in IDE. Most polyatomic ions will end in 8 or ite, but you can see right here, here's a couple of them. OH minus is hydroxide, CN minus is cyanide. So these are also polyatomic ions. Most do end in 8 or ite, but there are a few. Azide as well, IDE is another example of that as well, but most will do the 8 or ite. Now, earlier I told you that when you have a metal, you should never ever use a prefix. And the only place where that could actually occur, for example, is if the polyatomic ion actually has a prefix in its name. So, for example, if I did something with dichromate, it is possible to have a metal with a prefix, but it's because the polyatomic ion's name actually has a prefix in it. It's not that you put the prefix on there, it's just part of the polyatomic ion's name. So that would be the only place where you would actually see a prefix with a metal, but you didn't put the prefix on, it just kind of comes with the name of the polyatomic ion. Yeah. Any questions on that there? All right, let's try some here. Why don't we do, why don't we clear this out maybe? All right, so why don't you give some names here for, let's do Na2SO4. Let's do FeOH3. Let's do CuCr2O7. And let's do KHCO3. And then why don't you also write the formula for magnesium. Let's do chromate. Let's do sodium perchlorate. Let's do copper 2. Let's do copper 2 nitrite. All right. So names and then some formulas. So we'll look at the first one here. So I see a metal and I see a polyatomic ion. So once again, always as we talked about, when a metal is involved, that is where you should look at in terms of how you should name it. And really when you have a metal, the decision like we've been talking about is, do I need a Roman numeral or do I not need a Roman numeral? In this case with iron, do I need a Roman numeral? The answer is yes, because iron is again a transition metal. It's a type 2 metal. So here, what we want to kind of figure out is what is the charge on the iron. We do know the hydroxide is a polyatomic ion from that list. which is OH minus. It does have 3 of them, which means if we add all that together, that is 1, 2, and 3 on the minus, meaning that our iron should be a +3 in this case. I'll come down here. That will give us iron Roman numeral 3 once again for the charge, and hydroxide, the whole name of the polyatomic ion. Once again, does not matter how many you have. You just simply use the name of the polyatomic ion. Question on that one there. Next door to it is sodium, which is a metal, and sulfate, which is a polyatomic ion. Once again, we want to look at the metal, and the metal here is sodium, which is group 1, and that is a type 1 metal, which means it has a fixed positive charge, so do not need a Roman numeral on this. And that means I could just go right to the naming part. I'll go underneath it, sodium, and again, whole name there of our polyatomic ion, which is sulfate. What we got going on here is 2 sodium ions to balance out that -2 charge that's coming from the sulfate being our anion, and each of this Na pluses being our cation in this case. Again, it ultimately is still an ionic compound that needs to equal 0. Question on that one there. Next, we have Cu, which is copper, metal, and a little dichromate action happening there. So copper, which is a transition metal, means it's a type 2, and we do need a Roman numeral. So again, looking at the metal, this guy will tell us we need some Roman numeral action. And here we would look at the chromate, or dichromate in this case. It does have a -2, which means in this case our copper is a +2 to balance it out. And again, I'll go underneath here. That's going to give us copper Roman numeral 2, once again for the charge. And again, the whole name here of the polyatomic ion, which just so happens to have a prefix. And again, that's the only place where you'll kind of see that occur, because the polyatomic ion name has a prefix. Question on that one there. Yeah. Are you talking about this part of it? Yeah. So this part of it is a polyatomic ion. So that entire unit is all together, kind of covalently bonded, if you will. And the whole entire thing has a -2 charge. And it has a special name that this is its name in this case. Yeah. Yeah. Other questions? And it's why it's not called dichromate, because there's kind of chromate, which is CrO4 2-. So it's kind of a version of that, which is coming up. And that's where the di comes from, for the polyatomic ion part of the name. Yeah. But again, all polyatomic ions will have a special name that never changes. So it is just sort of like what its name is. Yeah. Other questions? So you should never add anything to it, and just use the whole name. Lastly, here we have potassium, which is a metal that is bicarbonate or hydrogen carbonate, which is a polyatomic ion. The metal important there, that is group 1, which means it has a fixed positive charge. That's all I need to name it, which means I got potassium. And again, you could go with hydrogen carbonate, or you could go potassium bicarbonate. They are both perfectly acceptable in this case, whichever way you want to kind of go with it. Question on any of those names there? All right, we got some names. Let's do some formulas. I see sodium. I see perchlorate. That's a metal and a polyatomic ion. We know it's going to be ionic, so we just need the basic units that make that up. So sodium is Na+, perchlorate is our ClO4-. Once again, this entire thing has a -1 charge. So ultimately we have +1 and -1, and that's all we need to do the formula. And this should be NaClO4. Again, you do not need parentheses around just one polyatomic ion, only when you got multiples. Next one would be copper Roman numeral 2 nitrate. That copper with a Roman numeral 2 means I do have a +2. Nitrate being NO3-. In this case, I got a +2 and a -1. So hopefully you can see you actually need 2 of those nitrates to balance it out, and that would give me Cu. Now that I have multiple polyatomic ions, I do need a parentheses, and again, the number on the bottom there, yeah. Any questions on that one? Again, that tells us we have 2 of the nitrate units, again, to balance out the copper with a +2 charge. Lastly here, magnesium chromate. Magnesium is a +2, chromate is CrO4 2 minus. So in this particular case, +2 -2, actually just need 1 of each in this case. And we'll get a little magnesium chromate in this case. So as you can see, for the most part, that's probably what you're going to see, metal with those polyatomic ions. And again, basically Roman numeral or no Roman numeral is what you have to decide. Once again, you do need to know the polyatomic ions, the names, and the charges and the formulas, obviously, to do it correctly. And like I said, that chart we were looking at should be up there on Canvas as well. Yeah. Any questions on polyatomic ions? All right, the last naming that we're going to talk about is actually acids. And acids are things, we use a scientific word of things that donate an H plus or a hydrogen ion. That's basically what makes up an acid, is the ability to release an H plus ion into solution so that it is floating around freely in that solution. And that's what makes it a acid. There's 2 types of acids. There's ones that do not contain oxygen, and there's ones that do contain oxygens. The ones that do contain oxygens are sometimes referred to as oxyacids because they contain oxygen, and they most often will have this bond here, this kind of OH bond, and that's a polar bond, and that is actually the hydrogen for oxyacids that pop off and makes it an acid. Basically, that's the one that gets released. For ones that do not have oxygen, the hydrogen is just attached to an anion, basically, and that's the hydrogen that comes off. So based on whether or not it has oxygen is also how we go about naming acids. So let's talk about how we do that. If your acid has no oxygen, you pretty much just roll with this formula here. You start with hydro, something ic acid. So for example, if I have HCl in the aqueous form, there is no oxygen here. That means we will start with hydro. For all acids, the cation for every acid is H plus. So H plus is pretty much your cation or positive ion for every acid that's present. That means we got Cl minus in this case, which is our negative guy. So this is hydrochloric acid. If you had HBr in the aqueous form there, which is a water environment, a solution basically. This is hydrobromic acid. Now you may be saying earlier, didn't we just talk about HCl like in the gas phase as being hydrogen chloride gas? And the answer is yes. When you take hydrogen chloride gas and you bubble it through water, you create the acid, which is HCl, which is hydrochloric acid. Most acids should usually, in their formulas, have the aqueous symbol next to it. And that implies that it's in solution, and that H plus is probably coming off and floating around in that solution. So usually when we write formulas for acids, we do put that AQ, which means aqueous or water environment. Basically, it's basically a solution. And we usually put that next to the formulas to indicate that we're talking about the acid rather than just HCl in the gas phase, which would be hydrogen chloride gas, just like HBr in the gas phase would be hydrogen bromide versus hydrobromic acid. Question on that. So no oxygen and it's an acid. That is your formula right there. The missing part is basically the negative ion. By the way, for this acid, H plus and Br minus, cation, anion, yeah, in the solution here. Now, when you do have an acid that actually has oxygen involved, you do have to kind of name it a little bit different than you do when you do not have oxygen involved. So if you're doing an acid and it has oxygen, the answer is yes. It will contain one of everybody's favorite thing that we just looked at, a polyatomic ion. So that acid will probably contain one of those polyatomic ions. As we just talked about, the polyatomic ions end in one of two ways, ate or ite. And that's also an important thing in terms of how you go about naming your acid. So if your polyatomic ion ends in ate, your acid name should be something ic acid. By the way, no hydro on this deal, yeah? So something ic acid here. So if I took HNO3, again, my cation is H plus, my anion in this case is NO3 minus. That is nitrate, ATE. This is nitric acid, yeah? You can remember you ate too much, you feel icky. Yeah, that's a good way to remember it, perhaps. So you could do that. If I take H2SO4, again, my cation is H plus, and there's two of them because my anion in this case is SO4 2 minus. That is sulfate. That would then be sulfuric acid. So if your polyatomic ion ends in ate, your acid name will end in ic in that case. That means that if your polyatomic ion name ends in ite, your acid would be something OUS acid. Also, no hydro. So hydro for acids are only for ones that do not contain oxygen. So no oxygen hydro. If you have oxygen, leave the hydro off of it, yeah? So if we take HNO2, cation here going to be H plus, anion going to be NO2 minus. That is our friend nitrite, ITE. This is nitrous acid, yeah, in this particular case. H2SO3. Cation going to be H plus and H plus, and we need two of them to balance out the -2 charge on our anion here. And our anion here is sulfite, which means this will be sulfurous acid. Yeah. So if your polyatomic ion ends in ate, your acid will end in ic. If it ends in ite, it will end in OUS. Questions on that there? All right, let's try a couple here, maybe. Oops, where'd it go? So let's say we have, let's see which one's here. Let's do, why don't you name these acids here? Let's do, and why don't you write the formula for phosphoric acid, hydrofluoric acid, carbonic. Actually, let's do carbon. Let's do carbonic acid. Carbonic acid. Let's do phosphorus acid. All right, so let's do names on the left there, formulas on the right. And here together, just to show you how to do these. Again, this is an acid. I see aqueous. I see no oxygen, which means I do know it's going to start with hydro. That is going to be S2 minus, which is sulfide. So this will be hydrosulfuric acid. Again, no oxygen, so we have the hydro in the beginning. This is an acid, H plus, and that is ClO4 minus. That is perchlorate. ATE means my acid will end in ic. We do still keep the front part here, and this is perchloric acid. Again, we do keep that front part from our polyatomic ion's name. Here we have H plus and ClO2 minus also contains oxygen. So that is chlorite. So ite means OUS on the acid, chlorus acid. Again, no hydro on anything that has oxygen in it. Question on any of those names there. HI, that has no oxygen, so that is hydroiodic acid, as that is iodine in the middle there, or iodide in the middle there. Now, when you have the name for an acid, you need to go backwards. Here's how you could kind of deconstruct it. We know that all acids, the positive guy is the H plus, so we need to find the negative guy. So phosphoric with no hydro means it has oxygen, and it's a polyatomic ion. Ic means it ends in 8, so if I just cross out the ic and put 8 there, that looks a lot like phosphate, right? And now I could just use phosphate's polyatomic ion formula, and now I can put it together to equal 0, which means I need 3 of those hydrogens, so H3PO4. And you should have the aqueous next up. Hydro means that it does not have oxygen. So all I have to figure out is the negative guy, which would be the middle part here. And that sounds a lot like fluoride. And then we could just put those together, one of each. And we will have our formula here. Carbonic acid, no hydro, which means it contains oxygen and a polyatomic ion. I could cross out the ic, and I know that should end in 8, and that kind of looks like carbonate now. And I could use the carbonate formula to get me my correct one. That is a -2, which means I need one more of those. H2CO3. Lastly, phosphorus acid, no hydro, so it has a polyatomic ion. Cross that out and put ite for OUS, and that looks like phosphite perhaps. And that's going to be PO3, 3 minus, along with our H plus. To balance it out, we will need 3 of those guys, giving us H3PO3 aqueous. Question on acids are acids in this case. Bases are really named the same way. They pretty